Good morning, good afternoon, and good evening to day 2 of the third Photonics online meetup. My name is Orad Reshef. I'm from the University of Ottawa in Canada, and along with Professor Andrea Armani from USC, I'm the co-chair of today's event. We are very excited to have you here today. We received over 1,000 registrations from all corners of the world, and today we are featuring 3 speakers from 3 different continents. So we are proud to say that we were able to present to you a truly international event. Let me begin by acknowledging the generous support of 4 organizations, this Photonics Media, the Center for Research in Photonics at the University of Ottawa, the Joint Center for Extreme Photonics at the University of Ottawa and the National Research Council, and the USC Viterbi School of Engineering. They have combined to foot the bill for this entire conference out of pocket, so that everything you see here, from the poster session to the booths in the career fair, is absolutely free to all participants. You can learn more about these organizations at photonics.com, at photonics.uottawa.ca, at extremephotonics.com, and at viterbischool.usc.edu. As a note, we are live streaming all of the sessions to YouTube today, but it is unfortunately with a significant delay of about a minute. So for this reason, our chairs will be much more likely to address any questions you might have if they're asked directly in Zoom. Questions are encouraged to be asked as early as possible in the talk, as opposed to at the end of the talk, so that all the other members of the audience will be able to vote on them, and comment on them. So let's try and make this event as interactive as possible given the circumstances. Speaking of interactivity, our little organization has come a long way in the last historical year. So new to this edition of POM is an entirely virtual conference center that also hosts a virtual poster session and a career fair yesterday. So in the breaks between these sessions, we invite all of you to join us at this conference center, which is in Gathertown, to network and mingle. Also, please fill in our event surveys. This is the best way to get your feedback to us to help us back to the organizers to help us improve all of the events for you. So if you need any of these links, so links to the Zoom stream, to the conference center, to the survey, as well as the conference program, all of these links can be found in your inbox in an email with the subject line POM21 important links. Now, we have an excited day planned for all of you with presentations on 3 topics selected by you, our audience, in a survey that we sent out a few months ago. Our 3 topics for the event today are on metasurfaces, on biosensors, and on frequency combs. And so now, without further ado, to kick off our metasurface section, I will now introduce our first topic share, Dr. Sean Rodrigues, a senior scientist from the Toyota Research Institute of North America. So he will be chairing the first session. Please take it away, Sean.
Thanks, Orad, and thanks for that introduction. Welcome everyone to the Photonics online meetup metasurface session. Again, my name is Sean Rodrigues. I'm a senior scientist at Toyota Research Institute of North America in Ann Arbor, Michigan. I'm very excited to be chairing this year's POM. We have a number of great speakers this year. Before we get started, I want to thank all of our attendees for joining today, as well as the rest of the Metasurface Committee, Mara Caglion from Tampere University and Arka Majumdar from the University of Washington for helping with the selection and planning process. Finally, I'd like to thank all of the POM team for working tirelessly behind the scenes to get this POM conference up and running, especially Dr. Orad Reshef and Professor Andrea Armani, who co-founded this conference. Before we get started, just a quick reminder to type your questions into the Q&A throughout the talk and upvote the questions you think are most important. Please don't wait till the end of the talk to ask your questions. So let's get into it. Our plenary speaker for this session is Professor Jason Valentine. Professor Valentine received a bachelor's in science and mechanical engineering from Purdue University in 2004 and a PhD in mechanical engineering from UC Berkeley in 2010. Later that year, he joined the faculty in the mechanical engineering department at Vanderbilt University, where he is currently an associate professor and the deputy director of the Vanderbilt Institute of Nanoscale Science and Engineering, VINS. Professor Valentine's past and current work includes the development of optical metamaterials, optical cloaks, dielectric metamaterials, and hot electron devices. His work has been selected by Time magazine as a top 10 scientific discovery. And at Vanderbilt, he has received an NSF Career Award, the Office of Naval Research Young Investigator Award, as well as the Chancellor's Award for Research. Please go ahead, Professor Valentine.
Thanks, Sean. Let's see here. share my screen. Okay. Yeah, so thanks so much for having me. Thanks to Orad and Andrea for organizing this. I remember actually 3 years ago talking to Orad about the first conference. Little did you know that every other conference in the world would be following your lead in 3 years. But it's a pleasure to be here. I'm going to talk about some recent work in our group concerning meta optics or metasurfaces for image processing. So, in terms of image processing and convolutional neural nets, these systems, deep learning and CNNs, have really revolutionized the way we process data and make decisions on data for a wide range of applications. We're going to talk about image processing today. So this would include things like object classification, localization, and segmentation. So telling where in the image the object is, recognition. So being able to locate objects in an image and classify them, image enhancement, medical image analysis. It's really revolutionized the way that we go about these things. But convolutional neural networks and deep networks and these new forms of digital image processing come at a cost. And it's really a computational cost. Okay, and we'll talk a little bit more about frame rates and limitations in frame rates in a second. But if you take a look at a deep neural network, it has obviously many layers. And the layers have different functions, for instance, convolution and pooling. And if you take a look at the most costly layers in terms of computation, those are the convolution layers. Okay, and so for this VGG16, this is a kind of a benchmark classification system. 99% of the computational time is involved in the convolutions. And in fact, most of that computation time is up front where you're dealing with a full image. So what happens is you go through this network and the data set gets reduced until you make a decision based on that data. But at the front of the network, you're dealing with a full size image. You're dealing with usually 3 colors. And so the majority of the computational costs are up front, okay? And these first layers are really convolutionally heavy. And so if you take a look at what's actually being done there, at the front of the network, you're identifying low-level features, okay? And as you move through the network, you get to higher and higher level features in, for instance, in classifying this image down here as an Audi A7. Okay, and what's important for the context of this talk is that these low-level features are really edges. Okay, these are really mostly edge filters, and this is oftentimes the most time-consuming portion of a classification network. In fact, there's a whole field of study just on edge detecting algorithms and how to do edge detecting more accurately and also faster. And so, for instance, just to give you some numbers, if you take standard data set, this is a standard edge detecting and kind of benchmarking data set. Take 2 very common ways of doing edge detection: the Canny algorithm, which is an analytical technique that would limit for this size of image your frame rate to about 15 frames per second, and a CNN-based, a convolutional neural network-based edge detector like holistically nested edge detection would limit your frame rates to about 2.5 frames per second. So those are pretty big barriers in terms of doing high-speed image processing, classification, recognition. So what I'm going to talk about today is a technique where we want to offload some of this computation into the optic. Okay, so to replace the front end of optical systems with a meta optic, and that meta optic would perform some portion, and today we'll be talking primarily about edge detection, some portion of the computation. The benefits of this approach is that the optic itself can be extremely high speed. The optics that we talk about today, the passive optics operate at the speed of light. Okay, they require no input power. Okay, so you're reducing power consumption and you're reducing the amount that you're needing to do digitally. You're reducing the computational requirements for the system. In addition to doing things in optics, you access additional information channels. Okay, so a typical focal plane array, you're going to get an intensity image and that's it. With metasurfaces, optics in general, you can access things like polarization, phase, momentum. Angle of incidence is a big one. We'll talk about that today in terms of edge detection. And so this can allow you to do more in the optics than you can on the digital side. So today I'm going to talk about 3 different areas, and I'm going to really make an effort to leave time at the end for question and answers. Okay, so I may pick up the speed a little bit at the end so that we have some time for you all to ask questions. But I want to talk first about passive edge detection and differentiation, compound meta optics, so doing multiple functions in one optic. I want to talk about recent work on dynamic edge detectors, so being able to image in bright field or in the edge mode at your choosing. And then talk about scalable fabrication of meta optics, essentially scaling meta optics to relevant apertures in an effort to reach realistic devices. Okay, so we're talking about image processing using optics, and this, in fact, is not a new area of study. Optical processing based on Fourier optics is a very old field, and takes advantage of the fact that you take an object and you place it, put that image through a lens, and that lens performs a Fourier transform. And so you can operate in the Fourier plane. You can do convolutions in the Fourier plane. Then you come back in the image plane, and you, let's say, for instance, you see the edges based on what you've done in that Fourier plane. Okay, I flipped the image here to make it upright, but it would be flipped upside down in reality. So we're going to talk about edge detection today, and in particular, differentiation. So if we took this system and we wanted to perform the second order derivative on the image, in the Fourier plane, we would take the convolution of, we take the Fourier transform of the image, okay, that's g of k of x, okay, and we would convolve it with a function of k. And for the second order derivative, we would multiply it by k squared, okay, the second order derivative. We then have another lens, do another Fourier transform, and get back into the image, but now it has been differentiated. Okay, to accomplish this convolution in this 4F system, we would have a filter where the transmission of the filter was proportional to k squared. And because this is the Fourier plane, or in the Fourier plane, this means that the transmission is proportional to the position squared. So you have a filter which blocked light at 0k, and then as you went to larger k, the transmission increased as the position squared, or k squared. Okay, so this is conventional technique for doing second order differentiation. This is a 4F system. You can actually make these correlators in many different configurations, but you'll notice they all have multiple lenses and they all are multiple focal lengths long. And so when we looked at this problem, essentially what we wanted to do is take the system, and instead of operating in the Fourier plane, let's make a filter, okay, a metasurface filter, where the transmission of the filter itself was a function of the in-plane wave vector. And we want to make a filter, in this case, which performs the second order derivative, okay? And so the transmission, or the transfer function, to be specific, must vary, or must be proportional to the in-plane wave vector squared. And if we can do that, and then we can put a lens on the backside, we can form an image of the second order derivative of our original image. So that's the goal, okay, here. And we aren't the first folks to think about this. There have been some other techniques for doing this, proposed and demonstrated in the literature. For instance, using surface plasmons, doing 1D differentiation, photonic crystals for 1D differentiation as well. What we really set out to do was, one, we really want to do all directions. We want to do 2D edge detection, but we also wanted to broaden the bandwidth, the operational bandwidth. Bandwidth is information, essentially. So you want to be able to get as many photons in the image as you possibly can. You'll want to be able to work at a relatively high numerical aperture. That's essentially your field of view of your differentiator. And we want to be able to make everything a flat optic, and we ask ourselves, you know, can we also make this thing dynamic? Can we switch between bright and edge imaging? All right, so to be specific, the ideal transfer function for performing the second order derivative, so performing the Laplacian on the incident field, okay, would look like this. So S and P are the S and P polarization components. You have your S in and S out, and P in and P out, the diagonal components here. You have off diagonal, which are polarization conversion components, okay, so converting from S to P, and those should all be a function of the in-plane wave vector squared. Okay, they all should be proportional to the in-plane wave vector squared. So the actual filter that we're going to make is going to be based on a pretty simple structure, silicon rods in a polymer, okay, and it's a periodic structure. It's perfectly periodic. It's a photonic crystal structure, and we're going to take advantage of the fact that for p-polarized input, okay, you can design it such that the transmission as a function of incident angle here, which is shown in the top right plot, can follow this kx squared within a certain frequency bandwidth. And I can explain more about how this works in the Q&A if you want, but essentially we have a guided mode in where we are using interference between the incident field and the guided mode to control the transmission as a function of incident angle. So it's p polarization, and we'll talk about this more in a second. S polarization, on the other hand, at that particular frequency range is completely reflective. So S is not going to actually perform the second order derivative, but it's going to be filtered out from the image automatically. We don't need to use polarized input light because the filter itself kicks out S polarized light. All right, so in our case, the actual transfer function we're getting is S is going to 0, and we're only dealing with P polarized light, and we have no polarization conversion, so the diagonal component is 0. Okay, and if you take a plot along that line versus kx, this is transfer function versus kx, you'll see that you follow this kx squared relationship for kx up to 0.3 or numerical aperture up to about 0.3. Okay, so again, that's connected to your field of view and also the throughput of your filter. Okay, so we have this dependence, and the phase also stays very, very flat. So we have the response we want, at least theoretically. Experimentally, this is what the filter looks like. So again, it's just silicon rods. And this is a Fourier plane images where the filter is off. Okay, this is actually just a wavelength where the filter is not providing the second order derivative. And you can see the Fourier plane is uniform, meaning we are allowing all angles in. And then we go to the working wavelength of the filter, and you see that the Fourier plane is now filtered. And if we take cross sections along the Fourier plane, you see that we have this kx squared dependence along the different directions in the Fourier plane. So we have successfully realized this kx squared transfer function up to a numerical aperture of about 0.3. Okay, so what does this look like in a real imaging system? Well, essentially what we've done here first is take a test chart, so Air Force test target, and we place the filter directly behind it. And we just image this in a conventional inverted optical microscope. This is the bright space or bright field image of the test target, so the wavelength and resolution. And these are the edge images. So these are with the filter in place now. And you can see that you see all of the edges of the image. And if you took a line scan through there, you would see kind of the double hump profile of a second order derivative every time you hit the edge. So it's an experiment and then the calculated second order derivative. So good agreement between the experiment and the theory. What's also nice is that even though we don't have the perfect second order derivative across a broad wavelength range, we have something which is close to it over about a wavelength range of about 200 nanometers. So you have a fairly high numerical aperture and you have fairly large working bandwidth for your filter, which essentially means throughput. You can get light through the filter for imaging real objects. So we wanted to do that, and so we take the system, and these are cells now. So these are onion cells, bright field image, and the differentiated image. So again, this is just filter on, filter off. You have no other parts of the microscope that we're changing, and this is again across a broader bandwidth. So you can see you get really nice clean images using this approach. Again, conventional microscope, just placing a filter in that microscope, and this could happen right behind the sample. It could also happen right in front of the camera. Okay. All right. So that was not a compound optic. That was a filter and a conventional lens. But what we would really like to do is get to a meta optic, which is comprised of multiple metasurfaces, where you can actually not only differentiate the image but form the image. So we can replace all of the components in the optical system with metasurfaces. And to do this, we use a technique which we've been developing in our lab for a while now, where we make multiple surfaces on separate substrates, and then we bond them together in an elastomer, okay? Similar to the way you would do like a lithography operation where you align a mask and place a mask on a surface. We're aligning surfaces and then solidifying the surfaces into multi-layer, multi-metasurface compound optics. And we've been exploring a lot of different functions, for instance, phase control at different wavelengths, polarization control, phase and amplitude control. So using very different types of metasurfaces placed together to get different types of functions, similar to the way you would line optics on a table, filters and lenses, for instance. So for this particular function, we're doing differentiation. We need to make the differentiator and we need to make the lens. And so these are images. These are patterned using e-beam lithography. And you can see peeling off the differentiator, we place it on top of the lens. What's also nice about this system is there's no need to align on the optical axis. Okay, so in a 4F system, you have to have your filter perfectly aligned along the optical axis. Here, the filter is uniform. So there is no there's no need for precision and alignment between the lens and the filter. You put them together and you can use this as the complete optical system. We have no extra lenses in this system. The meta lens is doing all the imaging and the differentiator is providing the edge information. And so this is bright field and the differentiated images, again, of those cells. So a little bit more noise in the images than in the inverted microscope, but that's really a function of the meta lens not being that optimized. So these are passive systems, right? You have filter on or filter off. You can change wavelengths to change the functionality from bright field to differentiated images. But we more recently have been thinking about how do we dynamically switch this? Because in a real image processing system, oftentimes you would want a bright field image. You don't want the unadulterated image and then the edge image, but in particular for image segmentation operations. Okay, so we would like to be able to dynamically switch between these operations. So, for instance, this is a design where the filter actually does nothing. So this is the working wavelength for TM polarization. The Fourier plane is uniform, so the filter is providing a bright field image. And then for this particular design, if you strain it, okay, so you take this is ideally in an elastomer. You take the elastomer and you stretch it. You can switch it to the period of the metasurface, which will switch you in to this second order derivative frequency band. Okay, so you change the transfer function by changing the period of the metasurface. And this particular design has this kx squared dependence over numerical aperture of about 0.25. Okay, so this is the design we actually want to try to make. We're already, in making the metasurfaces, we're already putting them in elastomer. So they're already in an elastomer, which we can strain. And so we just have to get the design right. So we built a little strain system on our microscope. So we're going to take the metasurface, peel it off an elastomer, stretch it, and look and see how the transmitted image changes as we strain. So remember, this really only works for TM polarization. So this is TE and TM, and at zero strain. Okay, actually this is not this is labeled strain, but this is essentially stretching. Okay, so 100% means unstretched. Okay, so it's the original, no strain on it. And so you can see both of the polarizations transmit uniformly across the incident angle. Okay, so they don't have really this kx squared dependence. As we start to stretch the material, so from 100% to 136% stretching, you can see that the TM polarization changes. Okay, so we go from something which is fairly uniform to something where we get this kx squared dependence at the 136% level, while TE polarization actually gets filtered out. So that transmission goes down and down and down as we transition into the differentiated image. And so you can look at the Fourier plane now, and we're using the input light is polarized. And so the vertical direction on the Fourier plane represents the TM polarized light coming through, and the horizontal direction here represents TE light. So originally, both are transmitted equally. And then as we start to strain the structure, okay, we notice that both go down at first, so the image gets darker, and then we transition into this kx squared along the vertical direction, so the TM polarization getting the kx squared dependence. And if we take a look at the actual imaging here, so we have bright field image, so unstrained, okay, 100%, and then we go to 136%, and you see that bright field transition to the edge image of these are the cells again. And if you take a look at another type of objects, this is kind of looks like a tube. Starts bright field, and then we go to the edge image as we strain the system. So we can dynamically change between a bright field and a differentiated image by changing the period of the structure dynamically. And you can start to imagine something like this being used in a segmentation network, where you take your object and you differentiate it, you feed that to a neural network, and you also feed the unadulterated image, the bright field image. And you're trying to figure out where in the image the objects are, or segment the image into its different objects. Okay, the last thing I want to quickly touch on is scaling these things. So being able to make them at large scale over relevant apertures. Okay, and this is something our lab has been working on for a little while now. We previously had developed a large area patterning technique using nanosphere lithography, where we assemble the spheres onto a surface of silicon. We shrink the spheres, and we use those spheres for an etch mask to make periodic patterns. And this is pretty straightforward. We developed this for, and we can certainly implement this for the edge filters. Edge filters are perfectly periodic. This allows you to get to aperture sizes which are relevant for common apertures in imaging systems, and they work really well. But the question is, how do you make something which is non-periodic? And so that's a technique which we have recently developed where we're still using nanoscale lithography, but instead of using nanoscale lithography directly as the etch mask, we use the nanospheres as lenses to expose a photoresist below them. And we don't give uniform illumination, but we use grayscale illumination, where we can change the intensity level as a function of position and thus change the size of the patterned rod as a function of position. And you can compare this to UV stepper lithography. We're not going to have as much resolution necessarily as UV stepper, or at least if you go to extreme UV. But there's a big benefit in terms of rapid prototyping because your mask size gets very, very small. So one of the problems with patterning trillions of unit cells is that you have very, very large masks, and it's actually difficult to implement those masks. They're so large. Whereas here, everything is translated into grayscale, allowing us to have very, very small mask sizes. And so these are some recent results of making lenses. Lenses are a nice kind of base structure to start with because you can characterize them really easily. So these are the grayscale pattern and then the actually fabricated lens and some imaging using those lenses. And the lenses actually come out really nice. So they have fairly high diffraction efficiencies, diffraction limit focusing, even though they have a few defects from the self-assembly process. So I think you can take these types of optics and scale them to relevant sizes. And that also really is the number of information channels. So the larger you can make the aperture, the more information channels you're going to have to work with in terms of image processing. So with that, I'll conclude and just say that I think there is a lot of prospects for replacing the front end of these image processing systems with optics, and you can get high speed while also reducing the power consumption and reducing the computational requirements. And again, I think you can scale these things to relevant sizes for doing these things. And so with that, I'll leave this up. Thank my collaborators and open the floor to any questions.
Great. Thanks, Jason. Thanks for such an excellent talk. There's a few questions coming in the Q&A, and I'm going to start reading off some of them. The first one is, what is the max strain you can apply without breaking the structure completely?
Yeah. So that would really be dependent on the material you're using. We're using PDMS here, and we are at about the max strain that we can get before tearing the PDMS. And it's actually more of a function of stress concentrations where you're actually contacting the PDMS rather than the strain limit of the PDMS in the middle of the array. So, but right now we're kind of at the max we can get with our strain device.
Great. Another one coming in from Corey Aiden says, amazing work, Jason. Can you tell more about the broadband operation? What is the bandwidth? I guess you showed operation between 1130 and 1180 nanometers in the first part of your talk. And then I can read the second question after that. So the operational bandwidth is a little bit hard to pin down because you don't have of course the perfect second order derivative as you get out into away from the center wavelength. So we've done imaging at around 200 nanometer bandwidth, and it looks fine. It's not the perfect second order derivative out at the edges. I think the more interesting question is, what's the bandwidth when you start to pair this with like a digital network to do segmentation? And because the digital network can correct some of the kind of error in the edges out at the edges. And so I think the question is, how accurate can segmentation be based on the bandwidth you're using? But it's about 200 nanometers kind of nominal, by eye, you could say. Gotcha. Great. We have another one here from Victoria Babicheva, and it says, if there is time, it'd be good to hear more about the modes under oblique incidence that Professor Valentine mentioned earlier in his Q&A.
Sure. Yeah. So I can show that. I have this slide kind of getting the little more of the nitty-gritty details of what's happening in the structures. So you can model this with coupled mode theory. That's what this is. But we've actually modified coupled mode theory so that the quality factor, the damping of the modes, is a function of the incident wave vector. Okay. So essentially, what you have is you have a bound state in the continuum or quasi BAC, depending on how you illuminate it. Here at 1200 nanometers, that's kind of away from our where we're operating, but we still the wavelength we're operating at, we still have some of that. We still have a fairly high Q. Okay, which is trapping light in the plane of the photonic crystal, but it's leaky. Okay, it's not a bound state, quasi bound, and it's that interference between the leakage and the incident wave that gives you this angle-dependent transmission. So you can model it with this coupled mode theory. We back out quality factors based on just periodic simulations like MPV-based band structure calculations, where you find Q as a function of in-plane wave vector. You plug that into the coupled mode theory, and you find like almost a perfect match between the full wave simulations and the analytical theory.
Thank you. Great. I have a question for you too. You've shown some great work with coherent light so far, but I was wondering if there's any chance that, or maybe what the next steps would be towards achieving incoherent light differentiation.
Yeah, so one thing that I think is interesting is taking advantage of the fact that with these structures, one of the benefits of metasurfaces is you can put a lot of different things on the same wafer, on the same aperture, very different structures. And I think one of the interesting directions is using that freedom to do multi-wavelength edge detection. So using, say, each filter for a 200 nanometer bandwidth, but having different center wavelengths in different regions, and taking advantage of the wavelength multiplexing as information channels. That's image processing. You're almost always, usually it's visible image processing. You're almost always taking advantage of RGB or some combination of those colors as information channels in classifying. So I think using distributed aperture type systems for increasing information channels is a really interesting direction.
Yeah, exactly. I think if there was a way to match the filter to the metasurface location, you could definitely have some good opportunities there.
And that also actually kind of plays to the benefit. So one of the problems with the lenses, right, is the lenses are also fairly narrow band in terms of their dispersion, and you can actually just you don't have to fight that if you do a distributed system like that.
Nice, thank you. So I'm looking at the questions again, and I see one. For your differentiating photonic crystal, you need this quadratic transmission profile. Did you design for that, or did you stumble upon it accidentally? How would you design for a different polynomial, for example?
Yeah, so that's a good question, and really we kind of stumbled on it. We were trying to make something dependent on angle. We were targeting K vector dependent transmission profiles, and we kind of stumbled on this one more or less. But that's an interesting question. How do you do what we're also very interested in is making more complex profiles, and I think you really have to go to some type of inverse design to do that. It's very challenging from a first principles standpoint to get that. In my experience, there are a different class. We've explored a bunch of different classes. We can do different types of. We can do low pass filters, high pass filters, band pass filters. We have designs for all those. But they're not necessarily like from first principles. It's more like stumbling upon these designs. So doing something more complex is probably going to get in the inverse design realm.
Right. Yeah, we had a great talk from Jelena Jukovic yesterday on inverse design.
Yep.
So let's see there. One more question here. From YouTube, Andre Andreev, what are the temporal parameters compared to Paco cell, for example? Does that? Yeah,
for the dynamic edge detectors, they're slow. I mean, you're dealing with strain. At least in this case, it's slow. You can imagine combining this with like a MEMS type architecture for modulation instead of using this kind of bulky, kind of this thing that the stage-based modulation. But it's never going to be super fast, at least for this particular approach. For something where you want to do fast, like frame rate type speeds, you're probably going to have to use a different technique like a liquid crystal or something like that to do the modulation. Because I mean, it's a photonic crystal, so we can change either the period or the surrounding media to modulate the response, and so liquid crystals would be a good option for that.
Excellent. Well, I think that about rounds it up with the time, and so I want to thank you again, Professor Valentine, for joining us today and sharing this great work.
My pleasure. Thanks for all the questions. That was fun.
Okay, so we had a number of great submissions this year for POM, and I'd like to just point out that The next 3 speakers that we have talking were in the top 5% of abstracts submitted. And I'd also like to remind the audience to please send your questions during the talk so that we can get plenty of discussion going on between everybody. So our first presenter is Charlie Rayman from the University of Exeter. Go ahead, Charlie. Thanks.
Okay, thanks, Sean, for the introduction. And good evening to all of you from the UK. I'd first like to thank all of the organizers for giving me this opportunity to present this work to all of you. And also congratulations on organizing another fantastic online conference. I'm sure it takes a lot of hard work behind the scenes. So I'm going to talk to you about how you can generate and tune artificial magnetic fields in metasurfaces. Now, this theoretical work was done in collaboration with Simon Horsley and Eros Mariani, both at Exeter University. So why are we interested in artificial magnetic fields? Well, if you look into the textbooks, you'll see that the interaction between charged particles and real magnetic fields gives rise to some of the most interesting and important phenomena in physics. For example, classically, we have this Hamiltonian for a charged particle in a magnetic field, which couples through the vector potential A. And this gives rise to the well-known Lorentz force, QV cross B, which can deflect charged particles into cyclotron orbits. And then in quantum mechanics, we have the Schrödinger equation, which gives rise to the Aronoff-Bohm effect. And then for large magnetic fields, we have Landau quantization of the cyclotron orbits, where the continuous spectrum splits into discrete energy levels called Landau levels. And this also gives rise to the famous quantum Hall effect. But what about photons? Well, photons are neutral particles. They don't have an electric charge, and therefore they do not directly couple to the electromagnetic gauge potentials. So all of these interesting magnetic field related phenomena remain elusive for photons. So this begs the question, can we somehow simulate these effects by generating an artificial magnetic field? And there have been several interesting ways proposed in order to do this, but in this work, we're going to focus on probably the most straightforward way, which is through strain engineering. Now, this concept originally emerged within graphene physics, where it was shown that the electrons propagating through a graphene membrane that had some strain pattern associated with it, then the electrons behave as if they were subjected to a large magnetic field, so-called pseudomagnetic field, which could mimic some of the properties of real ones. And the key advantage of this approach is that it has a purely geometrical origin, which means it can be translated into entirely distinct physical systems. So let's take a few steps back and try and understand why these pseudo-magnetic fields emerge in graphene. So graphene is a monolayer of carbon atoms arranged in a honeycomb lattice, as shown here. And the essential electronic properties can be captured by a very simple type binding model. So here we just consider the kinetic hopping of electrons between nearest neighbors with a hopping amplitude t. And the hopping amplitude is the same for the 3 nearest neighbors. So if we diagonalize this Hamiltonian, we obtain the famous band structure for graphene, where we have the conduction and valence bands that are degenerate at the high symmetry K and K prime points, the so-called Dirac points, where the bands disperse linearly. And as a result, the electrons are described by a 2D massless Dirac Hamiltonian. And this is what gives rise to many of graphene's remarkable properties. And this unique band structure is by no means an accident, and in fact is a direct consequence of the underlying symmetries of graphene. So the combination of time reversal symmetry and inversion symmetry locally stabilizes the Dirac points, this contact point. A gap cannot open up if you preserve these symmetries, at least locally. And then the free-fold rotational symmetry, the C-free symmetry, pins the Dirac points at the high symmetry points. So let's see what happens when we strain the lattice. And here we can see that the hopping parameters now become anisotropic. And as a result, we break the threefold rotational symmetry. And as a result of this, the Dirac cones decouple from the high symmetry points and shift in momentum space. And this shifting of the dispersion in momentum space is effectively described by a gauge field-like term in the Hamiltonian. And this so-called pseudo-vector potential depends on how you strain the lattice through the strain tensor epsilon. Now, this is the case for uniform strain. But if we want to generate a pseudomagnetic field, we have to remember that this is given by the curl of the vector potential. Therefore, we have to have a strain tensor which also varies with position. In other words, we have to break the periodicity of the structure in order to generate a pseudomagnetic field. Now, this phenomenon is not restricted to the physics of graphene, and in fact can be emulated in any system that emulates that shares the same underlying symmetries. So, for example, several years ago, Sergeyev's group demonstrated these pseudomagnetic fields in so-called photonic graphene, which is essentially a honeycomb array of evanescently coupled waveguides. And this system essentially simulates the type binding physics of graphene. So you have hopping of photons between neighboring waveguides due to the overlap of the evanescent field. And because they have meticulous control over the lattice sites, they engineered perfect trigonal strain patterns into the lattice, which gives rise to a uniform pseudomagnetic field, which points normal to the plane of the lattice. Now, the main drawback of this approach is that the pseudomagnetic field is usually fixed by the strain configuration that you imprint into the lattice design. So, for example, in this work, in order to change the pseudomagnetic field, they had to redesign and fabricate a new structure with a different strain pattern. And the strain patterns that you require are very precise. So this limitation raised a few interesting questions for us. So first of all, can we find some other mechanism, some other route to tuning these pseudomagnetic fields without having to reconfigure the entire lattice? And secondly, and more interestingly from my point of view, is can we find a way of switching off the pseudomagnetic field without having to remove the strain? Now, from the intuition that we've built up from the type binding models, this seems impossible, because if we distort the lattice in any way, we change the hopping parameters, and inevitably we get a shift of the Dirac cone. But at least in principle, this tunability is possible, because while we need to break the C-free symmetry of the lattice to have a gauge field-like term emerging in the Hamiltonian, the symmetry tells you nothing about the magnitude of this term. So it could be 0. But this depends on the specific details of the system. So if we want to have this tunability, we have to move away from simulating type binding physics, and in particular find a way of modifying the nature of the interactions between the lattice sites. And we can do this with metasurfaces. So in this work, we consider a minimal model of a honeycomb metasurface, which is just an array of interacting dipole emitters or antennas, with subwavelength nearest neighbor separation, such that the metasurface supports surface polaritons which are evanescently bound to the lattice. We also, for simplicity, just assume dipole moments that are oriented normal to the plane of the lattice. Now, the collective dynamics of this system is just described by a coupled dipole model, but it's well known that the radiative properties of emitters and antennas is not entirely determined by their intrinsic properties, but they also depend qualitatively on the surrounding electromagnetic environment. So we exploit this by embedding the metasurface inside of a cavity waveguide, and this allows us to modify the Green's function, which in turn allows us to modify the nature of the interactions between the dipoles. To elucidate this a bit further, we can decompose the Green's function into its longitudinal and transverse components, where the longitudinal component describes the short-range Coulomb interactions, and the real part of the transverse Green's function describes coherent interactions which are mediated by the cavity photons. And these tend to be long-range in nature, as shown here. Now, it's tempting to assume, because we have subwavelength nearest neighbor separation, that the near-field Coulomb interactions dominate the physics. Now, this is true for free space and for relatively large cavity widths, as shown by the blue lines here. But for small cavity widths, shown by the orange lines, you can see that the Coulomb interactions become exponentially suppressed for small cavity widths. And this is due to the screening effect of the cavity waveguide. In contrast, the photon-mediated interactions become more dominant. And this is because of the reducing mode volume as you reduce the size of the cavity. So you can see that just by changing the width of the cavity, we can tune the dominant dipolar coupling between short-range Coulomb interactions, and long-range photon-mediated interactions. Okay, using these coupled dipole equations, we have derived analytically an effective Hamiltonian that describes the Plaritons. So we have an effective Dirac Hamiltonian, and then these strain-induced pseudo-gauge fields. So we have a pseudo-vector potential A and also a pseudo-scalar potential phi. Now, the form of these pseudo-gauge fields are exactly what we find in graphene and artificial graphene systems because they're constrained by the symmetry. But in this case, the coefficients A0 and phi 0 have a very non-trivial dependence on the cavity width. So here I show how these parameters vary as we reduce the cavity width. And the blue lines correspond to the contributions from the short-range Coulomb interactions, and the orange lines show the contributions from the long-range photon-mediated interactions. And you can see a few important points here. So first of all, they contribute with opposite signs, and therefore they're always in competition with one another. They're always trying to shift the Dirac cone in opposite directions. And secondly, for large cavity widths, the gauge fields are dominated by the Coulomb interactions, and for small cavity widths, the gauge fields are dominated by the photon-mediated interactions. So if we add the contributions together, there must exist critical cavity widths where these contributions perfectly vanish, and it switches off the pseudo gauge fields. So this is quite non-trivial. So what it's saying is that you embed a metasurface inside of a cavity, and if you apply strain, at least at this critical cavity width, then no gauge fields are generated. Okay, so let's try and look at some of the consequences of this tunability. So if we consider a strain configuration that generates a uniform pseudomagnetic field, then the effective Hamiltonian predicts that the Dirac cone splits into these quantized Plariton-Landau levels, where the spectrum is given by this expression. Now, in previous studies, the spectrum is usually fixed by the strain configuration. But here, the Plariton-Landau levels depend qualitatively on the surrounding electromagnetic environment. So we can drastically reconfigure the Plariton-Landau level spectrum just by changing the cavity width. And specifically, the transition from Coulomb interactions to photon-mediated interactions is accompanied by this collapse and subsequent revival of the Plariton-Landau levels. Now, in order to verify these analytical predictions, we also developed a full multiple scattering theory. And here we plot the spectral function for a dipole located at the center of the metasurface, which is just the imaginary part of the effective polarizability, which takes into account all of the multiple scattering events. And we're particularly interested in this so-called Dirac region, which corresponds to the Dirac cone part of the Plariton spectrum. So this is for an unstrained metasurface with a relatively large cavity width where the Coulomb interactions are dominant. Let's see what happens when we strain the metasurface. What we see is emergence of a series of sharp resonant peaks, which do not emerge in the unstrained case. So these directly correspond to these strain-induced Plariton-Landau levels. Now, this is, again, the spectral function for the same metasurface, but now for critical cavity width, where we predict that the pseudomagnetic field is switched off. This is the unstrained case. If we now strain the metasurface, remarkably, we see no Landau levels emerge in the Dirac region. And in fact, there's very little qualitative difference between the strained and unstrained cases here. So it's a direct evidence that the pseudomagnetic field really is switched off at this critical cavity width. And then finally, here is a spectral function, again, for the same metasurface, but now a very small cavity width where the photon-mediated interactions are dominant. And when we strain the metasurface, again, we see the emergence of a series of resonant peaks, which directly correspond to the Plariton-Landau levels. So this verifies that the collapse and revival of the Plariton-Landau levels, which is induced by the cavity waveguide. So just to quickly summarize, what I've tried to highlight is that while the symmetry determines the form of the Hamiltonian and the form of the pseudomagnetic gauge fields, it's the interactions that depend the strength of that dictate the strength of the pseudomagnetic field in the metasurface, and we can exploit this by manipulating the surrounding photonic environment. So this also leads to some interesting questions. For example, how does this theory generalized to more complex antennas, such as split ring resonators and dielectric Mie resonators, which are prevalent in metamaterials research? And also, are there other ways of modifying the interactions by engineering different structured photonic environments? So, for example, embedding emitters in photonic crystals or mediating interactions with surface plasmons, etc. And also led to another interesting question, which we explored, is can you induce topological transitions using this method? And in a recent paper, which we've recently put on the archive, we have shown that you can indeed induce topological transitions as well. And just by changing the cavity width, you can switch the chirality of the topological edge states. So with that, I would like to say thank you for your attention and invite any questions.
Excellent talk, Charlie. Thank you so much. So we do have one question in the chat right now. The first question is, rather than use strain to modify the metasurface, would it be possible for one to use the dielectric environment, varying it in space to achieve a similar end to varying strain in space? Yeah, that's what it
says.
Yes,
in principle, yes. You essentially need to be able to smoothly break the C-free symmetry. That's a requirement. So whether you do that through the lattice sites or the environment, I think it should give rise to a similar effect. Yeah.
Great. And so I was kind of wondering, are there any radiant Landau level states as well, or?
Yeah, that's quite interesting. So we obviously consider sub-wavelength separation. So all of the plutons are subradiant and exist beyond the light cone. Whether or not these can exist inside the light cone is a good question, because if they just radiate, if they're leaky waves, then the Landau level peaks are just going to be broadened. So it's difficult to see how you could have these sharp resonances unless there's some kind of bound state in a continuum. So it's definitely an interesting question, but I'm not sure if it's been done yet.
Okay, thanks. And then I think we have time for one more question. Let's see. Can you articulate one more time, like what are the lengths of the cavity, or like the displacement that you take to turn it on and off?
So let's see if I can go back. So for this minimal model, again, we don't specialize to a particular realization. So we take point dipoles, and essentially for this system, the cavity width has to be smaller than the resonant wavelength in order to have a significant effect on the interactions between the dipoles. For example, on the right-hand side, this could be a cavity width of on the order of the spacing between the dipoles. But I don't think that's a strict requirement, but it's more of a feature of the minimal model that we have, because when you have finite, say, meta-atoms, then the cavity is going to have a far bigger effect because it comes near to the finite size meta-atom is going to modify the resonant frequency and modify the interactions. So I don't think it's a strict requirement. It's more of a feature of the minimal model.
Great, excellent. Well, thanks again for your wonderful talk, and yeah.
Okay, thank you.
So our next presenter is Nolan Lassaline from ETH Zurich. Nolan, go ahead.
Okay, can you see everything okay?
Yes, I can see.
Wait, and now I go to presenter view. Now it should be good. Yes.
Yes.
Okay. Yes. Hello, everybody. Good evening from Zurich, and thank you to the Photonics Online Meetup Committee for having me here to present today. And what I'm going to talk about is some new work that our group fairly recently came out with just a few months ago, which we call optical Fourier surfaces, as you can see here. And so being in the Metasurfaces session, sort of the common ground with a lot of the things that you're seeing today is that we are manipulating light with structured surfaces. And of course, this is something that humans have been interested in doing for a very long time. And in these two lenses that I show you here for this example, they're actually very different, but interestingly, they do have something in common. And that is that their function and performance, so what they do and how well they do it, are determined by their surface profile. And of course, nowadays, modern research is exploiting complex nanostructured surfaces to achieve these new functionalities. And this falls into the very broad class of diffractive optics. And these are things like metasurfaces, gratings, and holograms. And already we see that there's a very broad range of applications for these diffractive optics. So let's just take a quick look at that overview. And so for these various applications, we can sort of categorize them a bit into what they're doing. The first one being something we can call free space diffraction. And these are things like spectroscopic gratings or metasurfaces, where essentially we take photons from free space, they impinge on the structured surface, and then they diffract either to disperse or to form some type of image or focusing. The second general function is that of guided mode diffraction. And these are things like silicon photonic grating couplers or plasmonic grating couplers, where essentially we shine light onto a grating coupler from free space and it couples into a wave guided mode or vice versa. And finally, there are some functions that are happening completely on chip without the free space part. And so these can be things like photonic crystals and distributed feedback lasers, where you have a periodic structure in the surface plane, and the sort of action that they are having on the photons is completely in plane on your chip. And I think it's pretty obvious from this sort of slide that there are a very broad range of applications that these diffractive optics can have. And then this sort of poses the question, can we understand these very different functionalities with a simple and general common framework? And we can very easily within the wavy world of Fourier optics. And so Fourier optics is essentially the study of optical phenomena using Fourier transforms. And this allows us to decompose very complex problems into just a simple sum of waves. And so, for example, if we take one of those diffraction gratings, which I just showed in one dimension, what we can do is we can write down the inverse Fourier transform, which relates on the left our surface profile in real space, f of x, to its spatial Fourier spectrum, f of g, in frequency space on the right. And it's actually here in frequency space with which we can design and understand the diffractive properties of our elements. And this has been known for a very long time, and mathematically this is very beautiful and very simple. But in reality, we actually have this problem. And that is when you look at real gratings that we make in the lab, they're not wavy, but very often they have these sort of square profiles that we see here. And ultimately what this means is that these diffraction gratings, instead of having sort of a single periodicity, which we often think about them as having, they actually have a mathematical sum of many, many periodicities, shown again in the left on real space and in their Fourier spectrum on the right here in frequency space. And ultimately, this leads to two issues. And the first is that we have many of these unwanted spatial frequencies that you see here, and this contributes to loss in the diffraction. And furthermore, we can't freely add spatial frequencies that we might want to. And so this is posing limitations on the function of these diffractive optics. And ultimately, this is limiting their capabilities. And what would be really ideal would just be to have the ability to make wavy surfaces. And so here we introduce a way with which we can do that, which we call optical Fourier surfaces. And we do this by starting with very simple analytical design. So in this case here, sort of our most basic element is just a sine wave in one dimension. And what we do is we take this analytical function and we can convert it into a grayscale bitmap shown below. Then we use a technique known as thermal scanning probe lithography, or commercially known as the nanofraser. And we take this grayscale bitmap and we sort of directly pattern it into a polymer surface on our sample shown here. And then in our group, we use a process known as template stripping to transfer this to an optical material. In this case, silver, we're going to take a look at, where we just evaporate silver onto our template. We apply glue to the back of it, and then we strip it off. And this yields our wavy diffractive surfaces in the final optical material we care about. So again, in this case, silver. And what's really nice is when we do this, we can see that the surface profile has a very low RMS error value. So in this case, its error is only 1.8 nanometers compared to the function that we were trying to pattern. So it shows the accuracy of this approach. And now that we can produce these surfaces, the question becomes, how do we optically characterize them or measure their performance? And so we do this with a reflectivity measurement, and we do this by looking at how photons couple to surface plasmon polaritons along this metal surface. And so if we take this Fourier surface that I showed in the previous slide, so this single sine wave shown here, we have its Fourier spectrum down here in the inset, and just below, this is the measured surface profile with atomic force microscopy, where the blue circles are the measured data points, and the blue line is the desired function that we wanted to pattern. And then we do a reflectivity measurement in K-space. And so this is what I show down here. And so on the y-axis, we're sending in a broadband light source. So essentially over the whole visible, where we show the wavelength or the photon energy on the y-axis. And the x-axis, we plot the in-plane wave vector, which is related to the angle of incidence. And then we're doing a reflectivity measurement. So for every point on this map, we're looking at how much light is reflected or how much essentially comes back to us. And where it's dark, we see that 100% of the light is reflected. And where we have this sort of orange band here, that shows that we have a dip in reflectivity. And we attribute this dip in reflectivity to diffractive coupling between our incident free space photons and surface plasmon polaritons, which then propagate away along the surface and don't return. And finally, on the left, we show our experimental optical data. And on the right, we show a calculation from a simple analytical model we have. And we see a very good agreement between the two. And so this confirms that it works, that we can use these sine waves as sort of our basic building block. And then what we can do is we can freely add them together to achieve a desired optical response. And so, for example, the next step in complexity that we could take is to do the same thing as on the left, but now with 2 sine waves, as I show here. And again, when we look at the optical data, what we very nicely see is that these orange bands, again, corresponding to diffractive coupling of photons to SPPs, are doubled. So we essentially have 2 sets of these bands because we now have 2 sine waves in our surface profile. And of course, we can increase the complexity as much as we like. So here I show it with 3 sine waves with some particularly higher spatial frequencies this time. And even through all of this visual complexity, again, what we very nicely see when we do our optical measurement is that we have optical data, which very nice confirms the expectations from our analytical model. And this particular surface was shown here, or was chosen here to have these 2 stop bands or band gaps, which I will elaborate a little bit more on in a couple slides. And so I think now would be a good point to sort of stop and ask the very obvious question, okay, but how does this compare to traditional gratings that we've had for quite some time? And so a way that we can make a direct experimental comparison is we can take these analytical functions, which I just showed you, and we can convert them to a 2-level profile just based on a thresholding technique. And just to show you that this is like a relevant way to do it, the Feist group here at ETH, they have employed this function to make distributed feedback lasers for multiple wavelengths. And so when we do this process, then we can fabricate these gratings using standard techniques, so electron beam lithography and etching. And when we do this, we end up with gratings that look like this. So on the left in blue are the Fourier surfaces that I showed previously, and on the right are their binarized versions, again measured with AFM. And you can clearly see that a lot of the content that is contained in these wavy surfaces is sort of lost when we convert to the binary. And then it should be no surprise that when we shine light on these and we do the same optical measurements that we did before, we see that the optical response is strongly corrupted by the fact that we're no longer working with this nice wavy basis. And again, on the left is the same data as I showed you previously, and on the right is the data from the binary versions. And so what this sort of directly confirms is that with our approach in these wavy surfaces, we can precisely manipulate these electromagnetic signals. And then it, of course, begs the question, what else can we do with this? And so just to show some examples here, the first one, I'll start by revisiting these stop bands, which are important for a number of applications. And so what we can do for these stop bands is we can write out a surface profile here, where this amplitude of the second component, A2, is responsible for opening up this stop band. And so what we can do is fabricate a series of gratings where we tune this A2 from 0 to 25 nanometers. And when we do this, I show these grading profiles here in GIF format, so we can see sort of how the grading profile is evolving as this A2 grows. And what we very nicely see is when we take this optical data, we see that the width of the stop band, which is directly related again to this A2 parameter, is nicely opening and closing as this A2 parameter becomes larger and smaller, as shown in this format here. And so this, again, very nicely confirms mathematically that we have sort of our hands on all these tuning knobs and we can really precisely structure these surfaces for a desired optical response. And until now, this has all been done with sine waves modulated in 1 dimension, so along X as I've shown, but we know that surfaces are 2D, so can we sort of expand these capabilities beyond just this 1 dimension? And of course, we can do this and we can look at some interesting symmetries that arise. And so just to start with a basic example, if we take 3 sine waves rotated in the plane by 60 degrees relative to each other, shown here, overlaid on the topography, we can create essentially a hexagonal sinusoidal crystal, which exhibits 6-fold rotational symmetry. And then we can transfer this pattern to a metallic surface and we can shine light on it and look at the diffraction pattern. And again, these are reflectivity measurements. Again, on the x-axis, we plot kx, but now on the y-axis, we're plotting ky. So basically a 2D k-space image. And again, what we nicely see is that we have these reflectivity dips corresponding to diffractive coupling to SPPs. And these reflectivity dips very nicely overlay with the expectations from our analytical model, which is shown with this these white dashed lines here. And so now for this structure, we might ask ourselves, what about the rotational symmetry? And we'll find out that this 6-fold is actually the highest possible for a periodic structure. So can we increase it somehow? And the answer is actually yes, we can. And all we have to do is choose the appropriate combination of sine waves with the angular separation in between them. So for example, if we do this here for 6 sine waves separated by these 30 degrees, we actually end up with a quasi-crystalline pattern. And this has 12-fold rotational symmetry, and it has the interesting property of being quasi-periodic and no longer periodic. And this means that while it has this high rotational symmetry, it no longer possesses translational symmetry throughout the crystal. And then, of course, we can transfer this to our optical material. And when we do our reflectivity measurement again, we very nicely see that the 12-fold rotational symmetry contained in the surface profile is reflected in the rotational symmetry of our diffraction pattern that we measure optically. And again, it very nicely matches the expectations from our analytical model. And at this point, I think it gets perhaps a little bit abstract. And so just to sort of bring it back to earth here, we can ask the focus question. So what about some practical applications of these Fourier surfaces? And so for these applications at the beginning, I told you that square gratings had these 2 issues listed below. And now we have these wavy Fourier surfaces, and we don't have these limitations anymore. And so this would imply that we should be able to do 2 things. We should be able to make high efficiency diffraction gratings, and we should be able to now implement some new functionality that can solve an existing problem that wasn't able to be solved before. And so we can start with the high efficiency gratings. And the way that we measure these is we simply shine light on these gratings at normal incidence, shown here with Ki, and we look at the intensity of light that is diffracting into the 0 and the plus and minus 1 orders here. And just note that now we are diffracting to free space, and as I mentioned at the beginning, that is different than the plasmonic coupling that I was showing before, but otherwise it's still essentially the same thing. And so now when we shine this light on a sort of left-right symmetric sine wave, as I show here, and now it's quite a bit deeper than the previous ones, we can trace out these diffraction efficiency curves to see how the surface is responding. And so again, with this color code of red and green, we can trace the diffraction efficiency. So this is what I plot on Y here as a function of wavelength when we're sweeping this wavelength. And what we see is that for the plus and minus 1 orders, we have essentially the same intensity that is diffracting there because it's symmetric. And these each have roughly 50% intensity. And so when we sum these 2 up, we get this sort of overall diffraction efficiency of the surface of nearly 100%. But of course, for many applications, we're not interested in the symmetric diffraction, but we would actually like to break the symmetry and send all of our light into just 1 diffraction order, plus 1, for example. And so what we can do is similar to a Blaze grating, we can make a Fourier series, which is just the first 2 components of a sawtooth, an asymmetric sawtooth profile. And we can shine light on this and now see how it behaves. And what we nicely see is, compared to the case on the left, we are now diffracting essentially all of our light, so with nearly unity efficiency, into the plus 1 diffraction order. And the light that previously diffracted into minus 1 is now suppressed towards 0, shown in green. And so finally, so this of course shows we can make efficient gratings and we can steer the light in the direction we would like. And so finally, let's take a look at some new functionality. And so the problem we'll examine is that of multi-wavelength coupling. And so in this paper here, they nicely make a compact sort of waveguide integrated hologram. And what they do is they couple red, green, and blue lasers into their waveguide, which then they diffract from this outgoing grating to make their hologram. And the thing is, because they use a traditional grating with sort of a single periodicity, there's this angular dependence for all of these 3 colors, which takes this very nicely compacted device, and it sort of poses this frustrating limitation on the design of the optics to make it work. And so this is frustrating, and this is what we would like to eliminate. And so the cartoon of what we would want shows the situation here, where we want to come in the same angle of red, green, and blue. And we know from now our Fourier analysis that we simply need a spatial frequency corresponding to each color. And this produces such a grating shown here. And when we shine light over the entire visible range, all at normal incidence, what we very nicely see are these 3 prominent reflectivity dips, which correspond to the coupling of red, green, and blue photons, all at normal incidence. And ultimately what this shows is that these Fourier surfaces are mostly a very simple, but also a very powerful approach to solve some problems that exist in photonics. And then with that, I'll just quickly conclude. So we introduced here Fourier surfaces, these wavy diffractive surfaces. We use them to generate some improved diffractive optical elements. And I think most importantly, this opens up a lot of exciting new possibilities, not only for metasurfaces, but for optics in general. And finally, I would like to thank my co-authors listed here in bold and some other people below who helped me along the way. And I would like to thank you all for your attention. And I will now open up for any questions you may have.
Thanks, Nolan. What a great talk.
Thank you.
Let's see what the Q&A has. So I'll start at the bottom. We have a question from Pavel Shaptarenka, and it says, excellent talk, thanks. Perhaps building off of, they're building off of a previous question. Let me start with the first question then. So we see that it says, you've shown incredible control, but only for reflective surfaces. Is there any insight on how to extend this to transmission?
Yeah, that's a great question. So of course, the first thing that you would need to do is you would need to have a material that in the wavelength range you're working has basically transmissive properties and it won't just reflect it. And so what I can just very quickly show you is we did this in a number of materials. I only showed silver here for simplicity, but for example, if you look at the top right, we also did this transferring these to titanium dioxide, and this was done on a completely transparent substrate. And so if you do this process for the correct material, again, in this case, TiO2, you could also do this for transmissive surfaces, yes.
Oh, great. So jumping on to the next question, it asks, how straightforward is translating the surface into various dielectrics? Well, I guess that kind of solves it, right? I think you explained that just now.
Yeah.
So another question is, what's the largest angle you can tilt to? Does this correspond to the feature size?
I don't completely understand the largest angle you can tilt. Like of the substrate in an experiment, I guess you would, that means, or?
I think they mean like, what's the largest angle you could tilt the...
Like that you could diffract the outgoing beam to, is that?
That might be it, maybe.
Yeah. Okay, so if I assume that the largest angle means, what is the largest angle at which you can diffract? Maybe I can just use this cartoon here as a prop. So basically, the angle at which your outgoing light diffracts to depends on the wavelength of the light and the spatial frequency of your grating. And what we're showing here is that basically, we choose a spatial frequency such that we the outgoing light comes away at an angle that we can collect with our microscope, and then we can sort of quantify the intensity in that order. But in all of the plasmonic cases we showed before, in a way, that is kind of like a 90-degree angle where we diffractively couple to an in-plane mode, which propagates away along our surface. So you are sort of free to sweep that wavelength, or sorry, that angular range, depending on your wavelength and your spatial frequency, sort of anywhere that you can have photons, or in the case of guided modes, wherever guided mode can exist in your material, I would say. I hope that answers the question.
Great, thanks. And I think we have time for one more question. It's from Amit Agrawal, and it says, could you speak to scaling these optics to the centimeter scale?
Yeah, that's a really good question, and that's probably the biggest challenge that we have laying in front of us with these type of surfaces. So the limiting factor of how big we can make these surfaces is sort of twofold. So the first is within one patterning process, how big of a field can we make? And this is dependent on the piezo stage of our thermal scanning probe. So we have the probe on the stage, and it has a particular range. Now, this range is about 50 by 50 micrometers, so certainly smaller than this centimeter scale that the questioner asks. But there is no upper limit to how many of these fields that we can do in parallel beside each other and that we can stitch together. Of course, at some point, this will take longer to scale these up to a larger area. And there are perhaps some technical difficulties with how accurately can you stitch it for many of them put together. But this is something that we are looking at pursuing, and something, of course, for many applications that we need to look into. And the final point is that one of the biggest reasons that we chose to exploit templating to make these surfaces is because in the end, it doesn't matter how long it takes to make a template. As long as you make one good template, you can use processes such as imprint lithography or the templating that we show, and you can constantly and sort of faithfully reproduce many copies with the same surface without using very much time. So yeah, that's something we're looking into.
Excellent. Thank you. Well, that's about all the time we have for today. And I appreciate you taking the time to present today. Thanks. So our final presenter for this session is Lu Chen from the National Institutes of Standards and Technology. Dr. Lu Chen. And please remember to enter your questions into the chat anytime during the presentation. All right, Dr. Chen, take it.
Thank you for the introduction. And thank you for this opportunity to present on this fantastic online platform. The tutorial and the talks earlier in this session have already given a fantastic introduction on metasurfaces. So today I like to show how metasurfaces can also control the temporal waveform of ultrafast pulses. So ultrafast pulses are the shortest artificial events ever generated and have been widely used to study extremely fast phenomena in nature that would otherwise be inaccessible. So we work with femtosecond pulses that's 10 to the negative 15 seconds. So this is the timescale that we're talking about today. So the pulses are generated by a multi-octet Sapphire oscillator, which generates a train of short pulses in the time domain. The pulse width is only 7 femtoseconds. And in the frequency domain, each pulse contains millions of equally separated frequency lines covering a very broad bandwidth. For a 7 femtosecond pulse, the bandwidth is 200 nanometers. I just want to echo that the time domain and the frequency domain can be transformed to one another by doing Fourier transform. So in principle, to shape an ultrafast pulse, we can either directly modulate in the time domain or change the frequency domain, which by Fourier transform will also shape the temporal waveform. The latter here is actually much more practical because there is no modulator fast enough to directly manipulate on the femtosecond timescales. So what pulse shaping really means is to control the phase, amplitude, and polarization of each frequency line. The ability to shape an ultrafast pulse, most commonly its phase and amplitude, basically a scalar waveform, has led to numerous advances in modern science and technology. One application that forms the backbone of high-field physics and was awarded the 2018 Nobel Prize is the chirped pulse amplification. So the pulse is first stretched by manipulating its quadratic phase, spectral quadratic phase, then amplified and finally recompressed to generate extremely high peak intensities. Adding amplitude control makes the pulse shaping more comprehensive. So independent phase and amplitude control allows generation of nearly arbitrarily shaped scalar waveforms. For example, this is a pulse multiplication. The input is a train of pulses that are separated by the repetition rate, which basically is determined by the laser cavity dimension. So by applying a phase and amplitude modulation, the output now has a much higher repetition rate. In addition, light field is actually a three-dimensional vector. So being able to further shape the polarization degree of freedom brings chirality into the picture. And there are many applications that can be enabled by the temporal polarization shaping. For example, spatial temporal control of nano-optical excitations, where a polarization shaped pulse can locally switch the near field distribution in the vicinity of a nanostructure, or force molecular rotation using the technique of optical centrifuge. So here the light polarization continuously changes with an increase in rotation speed, or in this case, selective production of enantiomers from chiral molecules. So as explained earlier, we use a Fourier transform pulse shaper. A grating and a parabolic mirror perform the optical Fourier transform, separating and focusing different frequencies at different locations. A metasurface is positioned in the focal plane to provide a complex masking function to manipulate these spectral features. And the way we do that is, so this is a top view of the metasurface. We group the nanopillars into superpixels to address a set of frequency lines. And then another mirror and grating recombines the shaped frequencies into output pulse. The metasurface here offers many advantages, including high spectral resolution. So one big challenge when it comes to shaping ultrafast pulse is to cover such a broad bandwidth while still maintain a high spectral resolution. So here is a picture of our metasurface devices. Each line here is one metasurface. It's about 2.2 centimeters long, and we divide it into 660 superpixels. to cover a 200 nanometer spectral bandwidth. And here is a SEM image showing the nanopillars in 2 adjacent superpixels. There are other advantages like multifunctionalities at the single pixel level, which we will also explore later in this presentation. So using this approach, we have already demonstrated simultaneous and independent control of the phase and amplitude of a linearly polarized pulse, basically scalar pulse shaping, achieving operations like pulse compression, where we compensate and recompress a pulse back to its transform limited width, and high order distortion by adding a designed 3rd order dispersion to the input pulse to generate those wiggles, and also pulse splitting. So here, a single input pulse is split into 2 replicas separated by a design time delay. So, so far we have shown that metasurfaces can shape the scalar waveform of a femtosecond pulse. Next, I'd like to show how we can also control the temporal degree of freedom to achieve vector pulse shaping. So the design principle is explained by the Jones calculus. The input pulse is linearly polarized along the horizontal direction. Here we assume a Gaussian envelope. The metasurface itself can be explained by an anisotropic wave plate. So theta is the rotation angle of the nanopillar. Here we set theta to be 45 degrees. And phi x and phi y are the propagation phase along x and y directions. So after the calculation, the output polarization state is controlled by this propagation phase phi x and phi y. And this propagation phase comes from the fact that when light propagates through the nanopillar, it acquires an additional phase due to propagation. And this phase, the amount of this phase change is determined by the light frequency as well as the nanopillar dimension. So by controlling the lateral sides along x and y directions, we can design different phi x and phi y functions at different frequencies. And the temporal waveform of the output pulse is the Fourier transform of the shaped frequencies. So by properly designing phi x and phi y functions, we can design all kinds of different pulse shapings. For example, this is one possible polarization twisted pulse. The axes are time, P and S polarizations. So basically, this is a 3-dimensional electric field representation. The orange and cyan projections are the electric field amplitude for P and S polarizations respectively. The gray curve on the surface tracks the tip of the electric field vector. And we also have a color-coded Poincare sphere showing the temporal evolution of these polarization states. The colors represent time delay here. So a Poincare sphere is a graphical representation of the Stokes parameters, or in other words, the polarization states are represented by points on the surface of the sphere. For example, any point along the equator represents a state of linear polarization, with the directions being horizontal here, 45 degrees, 90 degrees, which is vertically polarized, and 135 degrees. The north pole represents right circular polarization, and the south pole is for left circular polarization. And any points in between are elliptically polarized. So here are our experimental results. From spectral interferometry, we can extract the spectral phase and the intensity for the P and S polarized components. And the experimental values match the design curves pretty well. And the temporal waveform of our measured output pulse is shown here. So the pulse starts with a polarization here at negative time delay, gradually approaches to a right circular polarization, then elliptical polarizations, then cross the linear polarization around time delay 0, then back to elliptical polarizations, but with an opposite handedness, and then finally reaches for a left circular polarization. or within the pulse itself. We can also achieve other types of polarization shaping by simply choosing a different design for the fax and phi functions. For example, here shows a set of twisted linear polarizations as a function of time, which are represented by the points on the equator here. And another pulse that follows a different circular path on the Poincare sphere, changing from right to left, then back to right circular polarizations. So far, we have shown that metasurfaces can shape the temporal profile of a femtosecond pulse, both scalarly or vectorial waveforms. The spatial wavefront so far has always been a Gaussian beam. So a Gaussian beam in, then a Gaussian beam out, but with a different temporal waveform. So one of the advantages of dielectric metasurfaces that we briefly mentioned earlier is the multifunctionalities at the single pixel level. So we also explore this property to show simultaneous spatial and temporal pulse shaping. So the idea is to superimpose a secondary two-dimensional phase function within each superpixel. So for example, a vertex spatial structure can be added to the temporal varying polarization by superimposing a spiral phase to fax and phi functions. What we would expect then is temporally, this is a polarization twisted pulse, and spatially we have a vertex beam. I'll just show some initial results as a proof of concept. Here we designed a vertex beam that carries a topological charge of 1. The design phase topography for phi x and phi y for the first 10 superpixels are shown here. In this design, we divide the entire spectrum into 200 superpixels. I'm only showing the first 10 due to limited space. So each superpixel has a spiral phase for the spatial shaping and an effective phase for the temporal shaping. And the bottom figure is an optical reflection image of our fabricated sample, also just showing the same first 10 superpixels. We also measure the interference pattern at one of the spectral components using a CW laser at 785 nanometers. And the interference fork confirms that the spiral phase can generate a vertex beam of charge 1 at this wavelength. So I hope I've demonstrated that the metasurface's versatility in shaping a large bandwidth near infrared femtosecond pulse, and its potential in simultaneously shaping the spatial and temporal degree of freedom using the single pixel multifunctionalities. There are still many opportunities out there, for example, in nonlinear optics, active transduction, and coherent control. So I'd like to acknowledge my colleagues, our collaborators, and my advisor who made this work possible, and thank NIST and University of Maryland for their support. And with that, thank you very much for your attention.
Great. Excellent talk, Lu Chen. Thank you.
Thank you.
So we're going to turn it over to questions. And there's one in the Q&A that says, what material is the metasurface made of, and what is the damage threshold?
Oh, that's a great question. Let me see if I have a slide for that. So the metasurfaces are made from silicon nanopillars on quartz substrates. The damage threshold is actually one of the advantages. Oh, sorry, not this one. Anyway, so our metasurfaces are made from all dielectric materials, which means the damage threshold is much higher compared to, for example, liquid crystals in spatial light modulators. So it has a great potential in like high energy pulses or high field physics. I don't have the exact number here, but it might be in the science paper we recently published.
No problem. Thank you. So I have another question for you. Is there some way that you're showing that you can do all these polarizations as they pass through in a single pulse? And so is it possible that you could do some kind of full Stokes polarimetry with a single shot? Is that feasible?
Yeah, that's another great question. Thank you. So the way we characterize our pulse is similar to when we shape it, because it's on femtosecond scales. So the way we characterize that is by directly measuring the spectral phase and intensity and construct the electric field in frequency domain. And then by doing Fourier transform, reconstruct the temporal waveform. So that's how we measure this. I guess it's a different way compared to measuring CW lasers.
I see. Nice. Thank you. And have you done any interactions with like chiral structures or probed any chiral structures in potentially biological samples as well?
We'd like to. So with the polarization shift pulses, now we have the temporal polarization degree of freedom added. So in principle, any molecules or materials that have an intrinsic anisotropy or chirality on the femtosecond scales, now this information can be extracted. So of course, if anyone has any specific applications in mind that they think might benefit from this exotic pulses, we are always interested in other possibilities.
Excellent, thanks. And we have one more question from the audience. It says, would you expect high nonlinear effects due to the pulse interacting with the nanopillars?
Okay, that's another fantastic question. Thank you. And that's the backup slide I had. So we did run the calculation, and the conclusion is we don't have any nonlinear effects. The reason is, first, the pulses are the wavelengths are separated along the x direction. So that's like different frequencies are on different locations. So and also by calculating the size of the focus for each superpixel and the pulse energy, what we get for the peak intensity is way lower than what would introduce nonlinear effects in silicon. So we do not consider nonlinear effects.
Okay, great, thanks. We have another question here. Have you explored or considered multi-material nanopillars?
Multi-material, that's definitely something we will be interested in. Yeah, we are not actively doing that, but we are looking into the possibilities of combining multiple layers in the nanopillars.
Great, excellent. Well, I think that's about all the time that we have for this session. Thanks again, Dr. Lu Chen, for your great presentation.
Thank you, everyone.
So I'd like to just wrap up this session and say thank you, everyone, for the great questions and participating in the chat. That concludes the Metasurface session. Please join us in an hour for the biosensors session at 3:20.